Hello everyone, welcome to another session. Today we will talk about explosion limits of hydrocarbons in terms of the chemistry and how this leads to combustion behavior. So hydrocarbons are typical fuels that we have in our everyday lives like gasoline, diesel, jet fuel, methane, natural gas. All of those are hydrocarbons, meaning that it's a molecule of some combination of hydrogen and carbon chains. So if we were to draw some limits in terms of pressure and temperature, like we did for hydrogen, it's known that depending on the initial starting pressure and temperature, you'll get a different chemistry. So somewhere here, you would have a limit where methane if you go to a higher temperature and higher pressure, methane is explosive. Specifically, if this were about 675 and then here 575, somewhere in this range, methane is explosive, and below that, it's not explosive. So different molecules have different limits because their structures give rise to different chemical kinetic pathways. So for a bigger molecule than methane, the next step up is ethane. It would look something like this. So this would be ethane, and propane, the next step up, has something weird. It looks like that. This would be propane. Propane. So as we see, they have different limits of explosion. Below these lines, it's not explosive. Above it is explosive, so depending on the molecule. So methane is CH4. The structure of that is 1 carbon, 4 hydrogens. Ethane is the next step up, C3H8, C2H6, and then propane is C3H8. So these are the fuels we're talking about. And what this means, what I'm going to do is show that, as we see from this plot, this is easier to explode than this. So what this means is like explosiveness. This is more explosive because it's easier in terms of lower temperatures and pressures. Explosiveness. It's easier to explode propane because if you expose it to a lower temperature and pressure, so it takes more energy to explode these, more pressure and temperature energy. And so also the bond dissociation energy. But in terms of the bond dissociation energy, for example, if you were to have methane, 1 methane surrounded by 4 hydrogens, something like this, and you were to dissociate this bond, for example, some change in energy, where you were to take one of these hydrogens off to leave the radical, you would have this unbonded electron plus some hydrogen radical. that's part of this explosive process. As we know, combustion is a chain reaction chemistry. You need to sustain these radical pulls that keep this chain reactions going, and in particular, explosiveness is characterized by accumulation of radicals, which when you have a chain branching reaction where you form more radicals than you start off with, that leaves you more pathways to have a lot of these radical reactions. So if you were to branch off, you would have even more reactions, and it'll feed back on itself and explode. So part of this process is forming your radicals, and the reason why methane is less explosive is because the energy to create this first radical from this mechanism is harder to do for methane than these. So the bond dissociation energy, it's higher for methane than this. So the bond dissociation energy, it's highest for methane, less for ethane, even less for propane. So because of that, it's more explosive. Okay. So so the harder it is to form harder to explode the fuel. So that's one factor, and we'll talk about the details next. And we'll also talk about why this happens here. What is up with this weird zigzag structure? It's due to chemistry. So what we're seeing here is that in this region, if we were to stay at one temperature, or let's stay at one pressure, if we were to increase the temperature at the same pressure, increase, it will become explosive. But then if we increase the temperature a little bit more, it will no longer be explosive. Then if we increase it a little bit more, it'll become explosive again. So what's up with that? Chemistry is what's up with that, and we'll talk about that soon. Before that, let's talk about different regimes. So 3 chemistry regimes, meaning 3 different sets of chemistry. So low temperature, low T, which means that T less than 800 Kelvin. You have slow kinetics and low thermodynamic stability. No flame or detonation is sustained. So you can have this type of reactions, but it's not really a flame if you stay in this condition. And so radicals are not stable thermodynamically or kinetically. It does exist, but it only contributes to it only affects this combustion behavior if it starts the things going. You can use low temperature chemistry to get you to higher temperatures, and then those higher temperatures will make the flame combustion behavior go. So intermediate chemistry which would be 800 to 1,000, that is where you actually have some chemistry. So for CH4, if you had this methane fuel, a chain initiation step would be so you would form two radicals from this. One is a little bit less reactive. These both are not as reactive as the others, but once you form this hydroperoxyl radical, you can recombine them to make this hydrogen peroxide, and that is a pathway to get to a more reactive radical. So if you were to decompose this hydrogen peroxide with the colliding with the third body, you can make these hydroxyls, which are very reactive. So once you form these hydroperoxyls, that's where you get this chain branching possibilities. So here, this is the key. The chain initiation leading to the formation of this hydroperoxyl radical can lead you to form hydroxyl eventually after a couple of steps. So the key is to start the chain with this at intermediate chemistry. Then you can start the process. You can form hydrogen peroxide, which is the point is here. These are the reactive ones. Because once you form this hydroxyl, you can have this heat release, which is that's the explosive part. If you just keep on increasing the temperature, you have these exothermic reactions. That's what allows you to increase the temperature. Increasing the temperature allows you to increase the kinetic rates of reaction. Increase the kinetic rates of reaction, you can form more radicals. You can form more water, which is exothermic. Then you can increase the temperature and go back and cause this thermal runaway and this explosion. So once you have this hydroxyl radical, you can go back to the fuel and release some energy by forming water. This is exothermic. So that's the intermediate chemistry. So let's talk about the high temperature chemistry. So greater than 1,000 Kelvin, you have open up these other avenues for chemical kinetic pathways. So one of them would be if you had this fuel at high temperature and any colliding partner, you could potentially create this first radical from this collision to give you the fuel radical and hydrogen atom. So this is a general important thing of combustion chemistry. We'll talk later, but it's each of these fuels, you take one of these hydrogens off and it forms a radical. And what's also present is the other radicals, so H, oxygen, are formed from different radical chain processes. And once you form those, you can attack the fuel molecule. So if you had this fuel molecule and it saw this H atom, you can form this radical again. If you saw this fuel, if this fuel radical saw the O atom, you can form this so this is a branching step. So again, this is this exothermic reaction. So this would be chain branching. This would be exothermic. So just having these two possibilities show you that you're going to form this branch of radicals which enable even more reactions to occur. Then once you start this possibility to form water, it's going to increase the temperature. That would speed up all these reactions even further, allowing you to branch more, chain branch even more, allowing you to release, form more water and increase the temperature, and so forth. That's how quickly you would get this increase in the temperature and let these explosive reactions go. So something like that. Okay. So the summary is that, without going into the details of these mechanisms, is that depending on how soon, how easily you can form these radicals, and you can form this thermal runaway where you would be able to induce all of these chain reactions, and if it leads to chain branching and exothermic reactions, it's going to just explode. And this might happen at intermediate temperatures. It'll be slower, but once you get to the high temperatures, it's going to explode. And the reason why this happens is because it just depends on how hard it is to form these first radicals. So going back, so for all fuels, I'll write down some of these key reactions which keep things sustained if you're high enough temperature. You need to keep this radical pull to keep all of these chain reactions going and chain branching going. And it happens above 1,000 Kelvin. Below that, you can get this conversion of fuel to products, but it's not going to be explosive, it's not going to be a flame, it's not going to be self-sustaining. If you can get these reactions going, and it's one option of combustion technology of converting fuel to high temperatures, which you can use for work, one option is to keep it at low temperatures because you can reduce pollution of nitrogen oxides and soot. And if you were to design a process, the only way to keep the flame going would be to, or one way is to have a catalyst. What is a catalyst? A catalyst is a magic-ish thing that you put in there so that the reactions, like it's a precious metal or some other exotic or special solid material that you would allow reactions to occur on the surface of this solid material rather than flowing through a reactor. Or you can flow over a surface. So the key is, so that is a process where surface reactions are occurring rather than gas phase reactions. But that's a different story, which is a kind of a specialized field of combustion, but it is one possibility in terms of improving, forming new technologies. So common for all fuels, hydrocarbon, are these very important reactions. If you had this hydrogen atom and it saw the oxygen in the air, you can have a chain branching. If you had this hydrogen atom and you had this third body with a third body, you can form this hydroperoxyl radical. And because this hydroperoxyl radical is the source of OH eventually, and if you were to have this first oxidation state of the fuel, because we're going to form CO2 eventually, but this is an intermediate to, this is the final step for heat release. So this is exothermic. So this would be the final step to getting this last bit of energy from the fuel, this exothermic step to form CO2. This would be chain branching. This would be a source of hydrogen peroxide. So these are key reactions to keep the flame sustained, or the combustion process sustained. Okay, so now going back to this explosion limits here, what is happening here? Why is this weird quirk in the temperature dependence? If you were to keep the pressure the same, it'll zigzag between explosive and not explosive. So that's the well-known so-called NTC region. What you have to know about if you want to design real combustion systems, depending on your fuel, all of them, like ethane even has a little weird thing about that as well. Depending on your fuel, you're going to have some negative temperature coefficient chemistry, meaning that if you increase the temperature, you're going to have more favorable combustion. If you increase, then all of a sudden it's going to become a disfavorable at high temperatures. That's what the negative temperature coefficient. So negative, all fuels have this. So propane is C3H8. One way to draw this would be in this organic chemistry, 1, 2, 3 carbons. each of them have a 4 bonds. So this is 2 bonds to carbon. So that's one way to draw this molecule. So if we were to define this combustion to be C3H8 plus oxygen, so one intermediate process would be this initial dissociation. So let's draw this as you have this molecule plus O2, and if you were to dissociate one of these hydrogens off, take one of these hydrogens off, you'll have the radical and you would form this hydroperoxyl. That's one important step here. So you take off the hydrogen, pop out, pick off one of those. Then, so this is called a propyl radical. I'll draw it right over here. Propyl radical is formed where then in general in chemistry you have this R radical is allyl radical, meaning some hydrocarbon that takes one of these hydrogens off. It starts off as a hydrocarbon, you dissociate one of these hydrogens, it forms an allyl radical. So that's what I mean about each fuel has this NTC region, and if we're talking about hydrocarbons, one short notation is using this big capital R, and each of them behave similarly, where you need to dissociate this hydrogen as part of the combustion chemistry, and you have this negative temperature coefficient behavior depending on the specifics of the molecule. So that's what happened in this case. So if in general we were to write different pathways, once you form this radical, these are different reactions that can occur. You can have this third body with a third body to form this RO2 radical plus M. It's a third body reaction. Or another pathway that can happen would be you would form this radical, and depending on the location, so different things can happen. These are 3 possibilities. You can recombine the radicals. So this would be so this hydrocarbon has different carbons. This is saying that you can form this radical either here or there, depending on the specifics. This one is saying that you can recombine these radicals to form a new molecule. So one important thing here is that RO2 radical is important because you can have chain propagating paths like this, or if it's not as explosive, it's chain propagating. But where it becomes explosive would be because it's chain branching. So the key is, once you form this allyl radical, it can go either to a less reactive pathway or a more reactive pathway. And each fuel has specific pathways, and in general, it's this allyl radical leading to this RO2 radical that can be either more reactive or less reactive. So it depends on the details of the fuel. Okay, so that's just a little bit of a flavor of how this hydrocarbon chemistry works. There's so many different possibilities, but one of the main factors is forming your first radical. Larger molecules are easier to dissociate their first hydrogen off. Because of that, it's more reactive. And to sustain this combustion process is going, you need higher temperatures to keep it going, and chain branching to keep it going. And there's two big ways to keep the temperature high, is by forming CO2 in an exothermic process and forming water in an exothermic process. Those are ways to keep the temperature high, which would increase, keep the kinetic rates high, which would allow you to form more radicals. And once you keep the chain branching high, chain branching allows you to get more reactions and so forth. That's how this self-sustaining process works. Okay, so that's all I had today. Thank you. See you next time.